right, so Unit 7 is a super short unit, actually. It's called Riemann Sums, and we really could have learned Riemann Sums before we did definite integrals. Some books do, some books don't. I choose not to. But we've approximated integrals using geometric shapes and signed areas. And we have found the exact areas using integral rules. So I like to do Riemann sums after the definite integral rules so you can kind of compare the exact area. All right. So the idea is we're going to use the area of rectangles to approximate the area under a curve. All right. So let's just kind of talk our way through the logic of this theory process. So if we had a curve, and let's just assume it was always increasing and above the x-axis, this shaded region would be the exact area, okay? And so we could go from A to B of our function, and we would be able to integrate and find it exactly, all right? But let's say before we knew definite integrals, we used geometric areas, and we just want to use rectangles, no triangles or trapezoids or any other shape. So if we use two rectangles, well, I want them to be uniform width. And so what I notice is, well, okay, if my curve is increasing and I use two rectangles because the height has to touch the curve, then this would be an okay, but it would definitely be a lot over, okay, for the integral value. What if I want to get a better answer? So what can we do? Well, what if we use four rectangles? So same thing. We want all the same width, and the heights have to touch the curve. And so this is a better answer, but it's still over. So how can I get even closer? What if we use 8? That's even better. What if I used like 20 or 50 or 100 rectangles? Well, the more rectangles we use, the more exact it's going to be. And so what happens is if I had like 100, I'll go back to the original drawing, they would be so tiny because they're so narrow that really my area, because I can just take one like right here, my area is going to be almost exact. So as the number of rectangles goes to infinity, it's almost the exact integral value, okay? And so that's the idea behind Riemann sums. So as we go through the process, now that we understand how Riemann sums work, we are using rectangles, but we shouldn't have to draw out the function, okay? It's not really necessary. All the rectangles do have to have the same width. Typically, because you're showing this work by hand, 8 is usually going to be the most that you have to show, all right? Notice the height is the function y value, all right? So that's kind of important to notice because some of the questions, especially on your student practice, will be in a different format, all right? So the more rectangles we create, the more work we have to do. And this could be by hand, this could be with a calculator. You really just have to be flexible. But the idea is this. We want the number to go to infinity. We're going to remember sigma means to add up. So we're adding up all those areas. And area is base times height. And really, because our base is going to be a uniform width, we can factor that out. And so we're really doing an infinite number of heights. That's the idea, okay? So a little bit of background. German mathematician Bernhard Riemann. Notice, I don't think that's too long ago. But anyway, he came up with this, so we'll give him some credit. All right, so the math of this process is pretty simple and straightforward. It's going to be length times width for the specified numbers. They will give you how many rectangles they want and the intervals and the function. All right, so I just included this so you understand kind of all of the theory behind it. On some of your homework, they might, instead of giving the actual value, they might leave it as a function, okay? So just keep that in mind and be flexible. But there's 3 different types of Riemann sums that we're going to focus on. One is called the right, and so what that means is that the right side of the rectangle is the one that's touching your curve. Now, this one can also be called inscribed, okay? So sometimes they won't always tell you if it's left or right, and it depends on the kind of curve. So I don't say that right means inscribed, okay? Notice if I had a curve like I was drawing here, so let's say that's f of x, and this is b, and that's a. If I wanted to draw my rectangles on the right, notice, see? These are going to be circumscribed rectangles. Okay, so depending if your curve is increasing or decreasing, it might be a mixture of both. It might be one. They might not say right. They might say using inscribed rectangles. And so you have to know if you want to use the right endpoints or the left endpoints. Okay, so same idea for left Riemann sums. If we want a left, that means that the height of the rectangle is touching the curve on the left. Now, on this graph, we notice, oops, and I missed that one right there. So let's act like that one wasn't there. This one has a mixture of both, but same idea. If I wanted, let's just say this is f of x. So if we want left Riemann sums, and it might be hard to tell until you get a couple more drawn. So really, if your curve is always increasing or always decreasing, it's either inscribed or circumscribed. If it's increasing and decreasing, you'll get a mixture of both. Okay, so I don't memorize that. I just know what type do I want, where do I want endpoint. I kind of make a graph and then I figure that out. All right. So one question that they might ask is they might just set up a Riemann sum and have you compare, are they going to be compared to the exact area? Would it be an overestimate or an underestimate? Okay, so keep that in mind. And it really depends on your curve. So if they're inscribed, it's typically an underestimate. If they're circumscribed, it's typically an overestimate. So the third type, and I have them all down here, sorry, is the midpoint Riemann sum. So what you notice is that the height of my rectangle is actually in the middle interval. All right, so this one will take a little bit more math to figure out what x value did they use to get that midpoint. So if this was 0.5 right here, that means it's in the middle of 0 and 0.5, so they actually used f of 0.25. And the same thing. From 0.5 to 1, they went in the middle, so they did f of 0.75. So notice that, okay? So they might use the notation with the function, or you might actually see the y value be flexible, okay? And I do have some of these on your student practice. I don't necessarily show that on my practice, though. So see, notice this, because it's natural log. So that would like, without a calculator, you're welcome to use a calculator. I just don't think it's going to be helpful. So that question number 5, you definitely want to use a calculator because look at those answer choices, okay? So I have 5 for you to practice. So let's go ahead and go through some. You would only be asked one of these questions, but I'm just going to do all 3 so you can kind of see what's different, what's the same, and things like that. So most of the functions are going to be pretty simple that you should be able to sketch by hand. So I know that's a parabola, it opens down, and my y-intercept is at 9. If I want to find out where it crosses the axis, we could set it equal to 0, but it really doesn't even matter. So I want to go from 0 to 1. So here's 0, and let's just act like that's 1, because I know if I plug in 1, I'll get 5. So, all right. So I'm only concerned with this region right here. And so I might just blow that up, but I think I should be okay. So we want to use, actually I will. I'm going to make this a little bit bigger. I'm going to do 1, and then we'll just go, I know that's not the best, but we want to use 4 rectangles from 0 to 1. So 1, 2, 3, 1, 2, 3, 4 parts. So half of that, half of that, half of that, The left RAM, so I want my base times my height. So my base is always going to be b minus a over the number of rectangles. So I get 1 minus 0 over the number of rectangles is 4th. And we notice that each of those is 0.25. But if it gets more complicated, you can go ahead and use this. So that's for my base. So 1/4. And then I'm going to put all my heights. I like to factor it out. So my heights are going to be on the left, because LRAM, oh, I'm sorry, I did not even talk about that. So left Riemann sum is abbreviated LRAM because it's left Riemann approximation method. And midpoint is MRAM, midpoint Riemann approximation method, and RRAM, right Riemann approximation method. Okay? So for my heights, if I want to use the left, that means when I go to draw my rectangles, the left part is where I'm going to get my height. And so depending on your curve, it might be more obvious, it might not. So I would exaggerate your curve if you're not sure for the under and overestimate questions. But I really want to do f of 0 plus my next height would be at 0.25 plus 0.5. And then, so 1, 2, 3. And then my last triangle height is 0.75. So notice I still have 1, 2, 3, 4 y values that we're finding. I don't go all the way to 1. That rectangle is covered by using f of 0.75. All right, so now if I want to find their values, we would substitute them into here. So a lot of times, just because this is time consuming, they'll just have you leave your answer as this setup. That's why I like to show it. So I get 1/4. We'll go ahead and find it though. So if I substitute 0, I get 9. That's the first height. And then 1/4. So if I plug in 9 minus 4 times 1/4 squared, I get 1/16. So 9 minus 1/4 is 8 3/4, which is 32, 33, 34, 35. Oops. 35/4 plus plug in 1/2, 9 minus 4 times 1/2 squared, which is 1/4. 1/4 times 4 is 1, so 9 minus 1 is 8. And then the last number I'm going to plug in is 3/4. So what is this? 8 3/4. This was 8. So if I plug in 3/4, I get, I'll do it up here, 9 minus 4, 3/4 squared. So 9 minus 4 times 9/16, which is 9/4. That's 36/4. So 36 minus 9 is 27/4. Which is 6 3/4. They're not all the same. It's not a linear decrease. So, and then if I wanted to find the approximation, I've got what, 17, 1/4. I'm just doing this by hand. 17 plus 35 plus 27 is 12, 162 over 4. And I'm not even going to combine those because I'm just going to multiply. So actually I should. There's so many choices. So if I divide that by 4, multiply for 8, 2, 68. So 68 plus 62 is 1/4 times 120. 130 over 4. So I get 130 over 16, which I should have reduced that. I should have reduced this, really. Oh my goodness, there's so much reducing. So, yeah, I should have reduced. I didn't. Well, if we divide by 2, I get 8. 2 is 65. Now, if I asked, because these triangles go over, and it's really the easiest to see on the last one, this would be an overestimate, okay? They don't ask, but just in case. All right, on right ram. So same idea, except, let's draw it up here. We've got this curve, and I'm totally going to exaggerate, and let's say that's 1. And so now we want the heights of our rectangles to be on the right. So I always start on the right to draw them. And then here, and then here, and then here. It was hard to tell that I started on the left intentionally on the last problem because, well, that's usually how you do graphs. So my height, same thing, is going to be base b minus a over n, which my base is 1/4. And then I want to set up my notations. So the first number we're going to plug in to get the height is actually 0.25 plus 0.5 plus 0.75 plus, we're actually plugging in 1. Now, I've done those heights on the other problem, so that saves us a little bit of time. So we get 1/4, and then 0.25, we got 35/4. Then we had 8. Then we had 27/4. And I have not substituted 1, so I get 5. And then we can just do all this math. So 1/4, 13 plus 62/4, which is 31/2. I'll get a little bit smarter. So 26/2, so 1/4 times 57/2, it looks like, which is 57/8. Now, those rectangles, because they're inscribed, that's going to be an underestimate. Probably not by much, though. And notice, my over is 65, and my underestimate's 57/8. Those are pretty close to each other, okay? The MRAM is really just about you finding what function values they separated. So I'm going to go ahead and we'll go ahead and finish this since I only have the one problem to do. So let's erase this because I definitely need a better picture to illustrate the idea. So I'm going to exaggerate. This is going to be 1. I know I have a curve going down. And we are still using 4 rectangles. So 1, 2, 3. So 0.25, 0.5, 0.75. But what happens is I want to use this middle point to go on my curve. And right here in the middle. So I like to draw my dots. So I have a little bit over and a little bit under. This one, same idea. So which one do you think is going to give the best answer? Yeah, midpoint. Okay. So it's still base times all my heights. So my base is still b minus a over n. So it's still 1/4 wide. This height, so I need to find out what numbers between 0 and 0.25. So you can divide that by 2 if you want, or add them up and take their average. So I know it's 0.125. And then between 2.5 and 5, once again, if you're not sure, you're just finding the average. If you're using a calculator, you want to do that. But I know it's 0.375, or really I'm going to add 0.125 to each of these, okay? Because I already found out that that's the value I need. Oops, there's a decimal there. And that'll find out where that height is. So f of 0.375 plus f of 0.625 plus f of 0.875. Now, that is a lot to plug in, so I'm going to go ahead and leave this set up, okay? So just because of time, I don't think the next 4 minutes is worth this value. If you want, you can convert these to fractions. So if this is 1/4 and this is 2/4 and then 3/4, well, this would be half. So this is going to be f of 1/8. I'll write it up here. F of 1/8. That's 2/8. So then I need f of 3/8, 4/8, f of 5/8, 6/8, and then f of 7/8, because those fractions are going to be easier if I didn't have a calculator to plug it into this formula. Okay, so be flexible. I thought I left a little note about the midpoint. I guess I didn't. I might have left it on. Well, I thought I had it on here, but if we would do the math, what we realize is that the midpoint Riemann approximation method is actually the average of the left and the right. So if I found those two answers, the midpoint's going to be in the middle. Okay. All right. So on your assignment, you are going to set these up. Number 1, number 2 and 3, I would definitely set that up. And really, you don't need a picture. Number 3, you don't really need a picture. You just need to know what values you're plugging in, so you can make a number line. And then same thing for 4 and 5. Number 5, you will need a graphing calculator though.